Hello students, welcome in today's lecture. In today's lecture, we are going to learn about mechanical properties of solids, NCERT section 8.5.2, and we will also solve two examples 8.2 and 8.4. This is disclaimer. Learning objectives. By the end of this lecture, you will be able to understand the concept of shear modulus. In today's lecture, we will cover first example 8.2, then 8.5.2 shear modulus, and last example 8.4. Alright. So example 8.2. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both of diameter 3.0 mm, are connected end to end. When stretched by a load, the net elongation is found to be 0.70 mm. Obtain the load applied using Young's modulus. Yc is equal to 1.1 into 10 raised to the power 11 Newton per meter square, and Ys equal to 2.0 into 10 raised to the power 11 Newton per meter square. This is the numerical value of Young's modulus for different material. Let's see the solution. Let's start by listing out all the information given in the problem. So copper wire, length LC equal to 2.2 meter, diameter D is equal to 3.0 mm. Here we need to convert it mm to meter. So just multiply by 10 raised to the power minus 3. So it will be 3.0 into 10 raised to the power minus 3 meter. Using SI units is crucial for consistency in calculations. Young's modulus Yc is equal to 1.1 into 10 raised to the power 11 Newton per meter square. The second is steel wire. Length Ls is equal to 1.6 meter. Diameter D equal to 3.0 mm. So again here we need to convert it mm to meter. So just multiply by 10 raised to the power minus 3. So it will be 3.0 into 10 raised to the power minus 3 meter. Both wires have the same thickness. Alright. So any difference in stretching comes from their lengths and material properties. Young's modulus Ys is equal to 2.0 into 10 raised to the power 11 Newton per meter square. Total elongation delta L is equal to 0.70 mm. So in meter it will be 0.70 into 10 raised to the power minus 3 meter. Alright. Let's continue with solution. So both wires are under the same tensile stress because they have the same diameter and are being pulled by the same force, that is F. This is important because it means the force is distributed equally through both wires. The figure here helps us visualize how the wires are connected and stretched together. So here the end to end, it means the end of the copper wire is connected with end of the steel wire. Alright, end to end connection means the both end of the steel wire and the copper wire are connected to each other. Let's define the force applied to the wires. We will call this F. This is the load that is causing both wires to stretch. It's important to keep in mind that this same force acts through both wires since they are connected in series. So recall the formula for longitudinal stress. We know stress is defined as force divided by area. So stress is equal to force upon area, where F is the force in newtons and A is the cross-sectional area in square meters. This formula helps us relate the applied force to the internal forces within the wire. Longitudinal strain, we can say strain is the change in length divided by the original length. So strain is equal to change in length is delta L and divided by original length, that is L. So this is the longitudinal strain. Alright. The important point here is this: strain has no units because it's a ratio of two lengths. Alright. We are continue with the solution. Cross sectional area A equal to pi into d by 2 whole square. Since both wires have the same diameter, alright, so here d is the diameter, so just divide by 2 and put the value of r, you will get the area. Substituting the values, A equal to pi into 3.0 into 10 raised to the power minus 3 meter divided by 2 whole square. Solving this, you will get A is equal to pi into 1.5 into 10 raised to the power minus 3 meter whole square. So solving this, you will get 7.07 into 10 raised to the power minus 6 meter square. This value will be used in the next steps to find the load. Alright. Now cross sectional area is same for both wires. The ratio of stress to strain is given by stress upon strain is equal to Y. So we have the formula: stress divided by strain equals Young's modulus or sigma over epsilon. Alright. So first let's recall what Young's modulus is. So we can say it's a measure of a material's ability to withstand changes in length when under lengthwise tension or compression. In simple terms, it tells us how much a material will stretch or compress under a given force. So the formula for Young's modulus is Y equal to F upon A divided by delta L by L. So it will be FL divided by A into delta L. So the change in rearranging the formula, you will get delta L, which is equal to FL divided by AY. This means the elongation depends directly on the force and the original length, and inversely on the area and Young's modulus. So elongation of the copper wire, delta LC is equal to F into LC divided by A into YC. Alright. Now elongation of the steel wire, delta LC is equal to F into LS divided by A into YS. So total elongation, delta L is equal to delta LC plus delta LS. Alright, sum of the elongations of the copper and steel wires. This makes sense because the wires are connected end to end. So the total stretch is just the stretch of each wire added together. So just put the values. So delta L equals to FLC divided by AYC plus FLS divided by AYS. This step combines both wires' contributions to the total stretch. So here we have factored out F over A from both terms, giving us delta L is equal to F by A into LC divided by YC plus LS divided by YS. Alright, this makes it easier to solve for force F, since all the other values are known or can be calculated. Alright, so total elongation delta L is equal to F by A into LC divided by YC plus LS divided by YS. So substitute the values in the above expression and you will be get the value of F. So simplify the expression, you will be get the value of F. So it will be 0.70 into 10 raised to the power minus 3 is equal to F divided by 7.07 into 10 raised to the power minus 6 meter square into 2.8 into 10 raised to the power minus 11 meter square per Newton. Alright. Now let's set up our equation to solve for the load. Here we relate the total elongation, which is 0.70 millimeters, to the force applied. The formula connects the force F, the cross-sectional area of the wires, and the combined effect of both materials, Young's moduli. So solving this, or we can say rearranging, you will get the F. So F equal to 0.70 into 10 raised to the power minus 3 into 7.07 into 10 raised to the power minus 6 divided by 2.8 into 10 raised to the power minus 11 Newton. So it will be F is equal to 4.449 into 10 raised to the power 2 divided by 2.6. F is approximately equal to 180 Newton. So hence load applied is approximately 180 Newton. Shear modulus. Let's start by defining shear modulus. Shear modulus is a measure of how stiff a material is when it's subjected to forces that try to slide one layer over another. Ratio of shearing stress to the corresponding shearing strain is called shear modulus of material. Shear modulus is also called the modulus of rigidity. Mathematically, we write the shear modulus as G equal to shearing stress sigma s divided by shearing strain. Here G is the shear modulus measured in pascals in SI units, and shearing stress is the force per unit area, also in pascals, and shearing strain is a ratio, so it has no units. So let's see. Shearing shear stress sigma s. So shear stress is the force applied parallel to the surface of an object divided by the area over which the force acts. In the figure 8.5, you can see a block being deformed by a force acting along its top surface. The force is F, that is acting on the top. So there is a small change, that is delta theta, and that is theta, small angle. Shearing strain. So shearing strain measures how much the shape of the object changes due to the applied force. It's calculated as the sideways displacement of the top layer, which we call delta x, divided by the original length of L of the object. Shear strain has no units because it's a ratio. Alright. So when we apply the force on the top of the box, so it will be changes the shape, and that from delta, that is delta x, small change. So now students, we will see an example which explains the concept of shear modulus and strain in clear way. So we will use a simple block to demonstrate how shear forces work. So imagine we have a block and we apply a force to its top surface, causing it to slide sideways. Take a look at this figure 8.5. Notice how the block deforms. This force is trying to move the top layer relative to the bottom, which stays fixed. This setup helps us see what shear stress and strain look like in action. Shear stress is defined as the force applied F divided by the area A of the surface where the force acts. So shear stress F divided by A. If we increase the force or decrease the area, the shear stress increases. Shear strain measures how much the top surface slides compared to the block's height. It's calculated as the sideways displacement delta x divided by the length L, or we can say height L. This gives us a ratio with no units showing the relative deformation. If the block is taller, the same sideways movement results in less strain. Shear modulus, represented by G, is the ratio of the shear stress to the shear strain. It tells us how much force is needed to produce a certain amount of sliding. A higher G means the material is more rigid and resists deformation. Alright. So, let's look at the formula for shear modulus. The formula will help us quantify how much a material resists being deformed by a shearing force. Shear modulus, represented by the letter G, is defined as the ratio of the shear stress to the shearing strain, and G is equal to shear stress divided by shear strain. Alright, mathematically G equal to sigma s upon gamma. So just put the values. So G is equal to F by A divided by delta x by L. So G equal to FL divided by A into delta x. Now solving for shear modulus. Shearing strain is defined as the change in angle theta between two originally perpendicular sides of an object when a force is applied. For small angles, tan theta is approximately equal to theta itself. Measured in radians, this approximation makes calculations much simpler and is commonly used in physics when dealing with small deformations. So G equal to F by A divided by theta, as you know, shearing stress is equal to force upon area. So finally we can say the shearing modulus as G equals to F divided by A into theta. This form makes it clear that increasing the force or decreasing the area or angle will change the shear modulus. Let's see. G equal to F divided by A into theta. Here G is shear modulus. So G equal to sigma s upon theta. Shearing stress sigma s can also be expressed as sigma s is equal to G into theta. Alright. So NSI units, Newton per meter square or Pascal. This is the same unit used for pressure and other types of stress. Now, shear modulus G is generally less than Young's modulus. So for most materials, G is approximately Y by 3. Shear moduli of a few common materials are given in table 8.2. Let's see. So material aluminum, brass, copper, glass, iron, and their shear moduli. That is for aluminum 25, for brass 36, copper 42, glass 23, and iron 70 with 10 raised to the power 9 Newton per meter square. Now, shear moduli of a few common materials, and that is lead, nickel, steel, tungsten, wood, and their value for lead 5.6, nickel 77, steel 84, and tungsten 150, and wood 10 with 10 raised to the power 9 Newton per meter square. Example 8.4. Square lead slab of side 50 cm and thickness 10 cm is subject to a shearing force on its narrow face of 9.0 into 10 raised to the power 4 Newton. The lower edge is riveted to the floor. How much will the upper edge be displaced? Shear modulus of lead is equal to 5.6 into 10 raised to the power 9 Newton per meter square. Let's see the solution. Here, the lead slab is fixed at the lower edge and a force is applied parallel to its narrow face, causing a shearing effect. Look at figure 8.5. It shows the force direction and how the slab might deform. So here, the given terms, side of the slab is 50 centimeter, or in meter it will be 0.5 meter, and thickness T equal to 10 centimeter, in meter it will be 0.1 meter, and shearing force F equal to 9.0 into 10 raised to the power 4 Newton meter, and shearing modulus G equal to 5.6 into 10 raised to the power 9 Newton per meter square. Alright. So area of the face parallel to which this force is applied is A equal to L into T. So just put the values 0.5 into 0.1 meter. Solving this, you will be get 0.05 meter square. Alright. Now use the formula for shear modulus G equal to FL divided by A into delta X. So delta X is equal to FL divided by AG. Alright. So substitute the values and calculate. So solving for delta X, so delta X is equal to 9.0 into 10 raised to the power 4 Newton into 0.5 meter and divided by 0.05 meter square into 5.6 into 10 raised to the power 9 Newton per meter square. Solving this, you will be get 9.0 into 10 raised to the power minus 4 divided by 5.6. So delta X equal to 1.61 into 10 raised to the power minus 4 meter. Students, now we are discussing summary. So shear modulus is the ratio of the shearing stress to the shearing strain, also known as modulus of rigidity. For a wire under load, total elongation is the sum of the individual elongation of the different segments. It will be delta L is equal to delta L1 plus delta L2. Shear stress is calculated as force per unit area parallel to the surface. It is sigma S is equal to F by A. Shearing strain is measured as the ratio of the transverse displacement to the original length, delta x by L. Fundamental equation for shear modulus is G equal to FL divided by A into delta x. For small deformations, the shearing strain is simply the tangent of the angle theta, which is the angle by which the shape is distorted. Shearing stress can be expressed as sigma s is equal to G into theta, where G is the shearing modulus. SI unit of shearing modulus is pascals or Newton per meter square. Shearing modulus is approximately 1/3 of Young's modulus, Y by 3. Materials like tungsten and steel have a higher shear moduli, while lead has a relatively low shear modulus. Now we have a practice questions. First, if a force of 100 Newton applied to a surface area of 0.02 meter square causes an angular deformation of 0.01 radian, calculate the shear modulus. Material has a shear modulus of 30 into 10 raised to the power 9 Pascal. What shear stress is needed to produce a shear strain of 0.002? If Young's modulus of a material is 90 gigapascal, what would be its approximate shear modulus using the relation? Alright. Calculate the shear strain when a shear stress of 5 into 10 raised to the power 6 Pascal is applied to the steel. And rectangular block experiences a transverse displacement of 0.5 mm when its top surface of area 100 centimeter square is subjected to a force of 1000 Newton. If the height of the block is 10 centimeter, find its shear modulus. Alright. Thank you for your attention. I hope this lesson was helpful.